something to clear up before we go too much further, because I don't think I said it on the previous video, and that has to do with ATP as a high energy molecule. So ATP is a rather high energy molecule, right? It's not the highest high energy molecule within the cell. Actually, phosphoenol pyruvate has higher free energy than ATP. But if ATP is a very uh, high energy molecule, and it's rather unstable because of the strong electrostatic repulsion because of all of the negative charges on the phosphate group. So it's a very high energy molecule. So why doesn't it spontaneously hydrolyze, fall apart, and progress down to, right, here's where you'd find ADP and PI. So obviously much lower free energy. If you think low energy, that means higher stability. Negative delta G. So if we look at the hydrolysis of ATP, obviously this is going to be a negative delta G. That means that it's a spontaneous reaction. So why isn't ATP spontaneously falling apart all over the place? And the reason is because of this energy barrier. This is the amount of energy that needs to be put into the system, either in terms of thermal energy into the system in order to move to what would be the transition state. So this indicates the free energy at the transition state of the reaction. So the transition state is an extremely unstable intermediate. It's an extremely unstable reaction intermediate with a very, very short lifetime, very unstable, about the time of a bond vibration. And in order for us to move from reactants to product, we need to add this amount of activation energy into the system. Now, this is showing you the activation energy needed in an enzyme catalyzed reaction. So enzymes lower activation energy by a number of strategies that we cover in Biochem 1, so you'll get there eventually. But in in the non-enzymatic reaction, this activation energy is very, 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 very high for the hydrolysis of ATP. And because of this very, very high activation energy for the uncatalyzed reaction, we say that there is a kinetic barrier to thermodynamic stability. So ADP and PI are, they have a low free energy, and so they're more thermodynamically stable. ATP has a high free energy, so it's thermodynamically unstable, but there's this huge kinetic barrier here that's preventing ATP from moving into this transition state. And in that transition state, we need to have a nucleophile. For example, an oxygen, right, that is presented in the context of an alcohol group. And of course, if we wanted to substitute a hydroxide here, we could, and we're aqueous based systems. So, in theory, we could have hydroxides acting as nucleophiles necessary for hydrolysis of ATP, but we don't. We'd have to form a pentameric intermediate, and this is just a very high energy structure. So we really need an enzyme to help us achieve that pentameric intermediate for the nucleophilic attack, right, on one of our phosphates in ATP. So to sum this up, because delta G's, and that should be a delta, right, capital D, Greek capital letter D, because delta G's are additive, we can couple unfavorable reactions to favorable ones and then move the reaction forward. So on the y-axis here, we have free energy, usually measured in terms of kilojoules per mole. And we are looking at this reaction where we have the phosphorylation of glucose to form glucose 6-phosphate. Glucose 6-phosphate has higher free energy than plain old glucose. And so this is an endergonic reaction. It is thermodynamically unfavorable to proceed in the forward direction under normal conditions. And if we look here, the products have higher energy than the reactants. The second reaction that we consider is the hydrolysis of ATP, which has a wonderfully large negative delta G. And so because the sign on this delta G is negative, and you can see that it's greater in magnitude than the delta G, the positive delta G, for the phosphorylation of glucose, we can couple these reactions together and we end up with a net, right? This is coupled reaction. We end up with a net overall negative delta G, and so we can then get this reaction, reaction 1, to move forward because of the energy release when we have the hydrolysis of ATP. So if we look at, why is this possible? Why is coupling of this reaction possible? It's because of the difference in free energy of the reactants and the products. So what is the difference? So there's our overall net equation. And if we look at the relative concentrations of the reactants and the products, we'll see that there is less free energy in the products as compared to the reactants. And so overall, we're able to move this coupled reaction forward within the cell. So delta G, there's a lot of different expressions here for delta G in its many forms. Let's look at this delta G right here, which is the delta G that is the actual free energy change. And this actual free energy change is found using the equation delta G equals delta G prime naught plus RT ln output Q, right? Where Q is the mass action ratio and Q is equal to the concentration of products over reactants at the start of the reaction. That's very important, at the start of the reaction. So this is the expression for delta G, right? This is the expression for delta G. Now let's address delta G naught and delta G prime naught. Delta G naught is the standard chemical free energy change. Delta G prime naught is the standard biochemical free energy change for any reaction. Delta G, you measure, can be experimentally determined as well. And this is variable, right, based on the system. Both of these, delta G naught and delta G prime naught, are constant, and you look them up in tables, and they were, right, experimentally determined, but they are constants, right, and you look them up. They're unchanging. And again, in that equation, delta G equals delta G prime naught plus RT ln Q, whoops, right, RT ln Q, we need to look this value up in a table in order to determine delta G. So both of these, both of these are standard values. And what's the difference between them? The difference between them is the conditions under which they are measured. So if we look at standard chemical conditions, so the conditions used to measure delta G naught, these conditions are not compatible with living things. And I think I've told you this in the past, so this is kind of a quick overview. We're assuming all reactants and products at 1 molar at the start of the reaction. And that means all reactants and all products. So water present at 1 molar, hydrogen ions present at 1 molar, and those conditions are not compatible with living things. So standard biochemical conditions are the conditions which are compatible with living things. And so we are looking at 298 Kelvin, which is 25 degrees Celsius, obviously compatible with life. We are ignoring water. So water is a great participant, right, in many chemical reactions, and we ignore the concentration of water in reactions. And we can do that because water is about 55.5 molar. And so essentially that's an infinite concentration, right? And we're aqueous based organisms, so we can ignore the concentration of water. It's fairly constant, so it's fine to ignore that. We'll assume hydrogen ions are present at 1 times 10 to the minus 7th molar, which is pH 7, compatible with life. We also assume magnesium to be present at 1 millimolar if it is a factor in the reaction. In addition to referring to this delta G prime naught as the standard free energy change under biochemical conditions, you can refer to this as also the standard transformed constant.